Hey everyone, this video is about invariance, specifically differential item functioning, which is table 30 in Winsteps. So there's lots of different aspects of measure invariance. And what we're talking about is that we want everything to be the same across groups. So we don't want something about somebody to influence their answer on a response or to influence the way that they're viewing the construct as a whole. So if you take instructional equation modeling with me, we talk about configural, metric, and scalar invariance. What we're talking about here is differential item functioning associated with Roche and IRT analyses. And what we're talking about here is that the items don't vary on the item characteristic curve. So we got that nice S curve, and we don't want that to vary based on group. And the implication of that, so what we're really saying and the way that we talk about that, is that the item functions the same across the groups. So invariance means that the person positions, the item positions, all kinds of things, the whole model essentially is invariant, so it does not vary by time, groups, ability levels, etc., etc. And we see this in DIF, differential item functioning. So if we don't have invariance, if we see things that vary, we see this, we call it DIF. And it could be a lot of reasons that we get DIF. Typically, it's what we see in social sciences is that the ruler isn't the same for all people. It could be a translation issue, it could be an ability issue, it could be a bunch of different things that are influencing the ruler is not invariant. And it could also be that we have certain persons, that there's something about them that is making them answer differently to a set of items than the norm, than the population. Those are harder to find, by the way. And so what matters here is that if we don't have invariance, it becomes a lot more problematic if people are viewing things differently, and we have a lot less reliability and validity. So differential item functioning ends up being a t-test. This is really similar to ANOVA. So we find a difference somewhere, and then we have to go group by group with ANOVA's post hoc analysis, trying to understand individual group pairings and who is different from who. There's a lot of different, again, reasons and kind of ways that we see this occurring. So it could be that one group is performing usual, like the typical attitude or ability level, and we have one group that's outperforming them, or another group that is underperforming them. That would show up as DIF. It could be that one group some items are just more difficult for one group than another. It could be that they are just completely functioning different. It could be that one group has special knowledge that we weren't accounting for. There's all kinds of different reasons that we'll see this. And what you will be happy with is that it's statistically significant. So this is not cutoff values that we can break and cite somebody else, or kind of a range of cutoff values that if this is the ideal and if it doesn't work, we can use this one. This is 0.01 significant or not significant. And again, we're going back to the kind of the one-to-one comparison like we would in a post hoc for ANOVA. We're not looking at necessarily fairness, but what we do see is that a lot of times one group is favored over another group when we see differential item functioning. And this can be influenced by the size of that effect, and of course by the size of the classification groups. So if you have one group that is really small compared to another group that's really large, now we're looking at an unbalanced design, and you have to think about how much you trust that. Again, it's the exact same thing with ANOVA when we would have a group of 5 compared to a group of 100. Even if I find a significant difference between those groups, I'm not going to report it because the statistical validity of that is questioned. And I don't want 5 people to represent an entire group. So I tend to want either equal groups, at least 20, 20, 20, or if I have really large groups, then I would want to represent groups by at least 30 people. What is really cool about differential item functioning is that it's not influenced by model fit. So you might actually see times and see articles that are completely focused on diff, even though their model fit isn't that great. So we can still see group differences, even if the model isn't perfectly unidimensional, and some items don't fit the model very well. So this is a t-test, but it's like a post-hoc where we do lots of t-tests all at the same time, which helps us adjust for type 1 error. And this is the table. So we're looking at table 30 in Winsteps. You are going to scan for 99% confidence. So you're looking for p less than 0.01. This table does continue over and down, but these are the columns that we're looking at. So we're looking at the Welch t-test. You find the probability line, put your finger on the screen, and scroll through this table looking for ones that are less than 0.01. So if we've looked at this one specifically, we scan the p-values, we see that this one is significant, we scroll over. So this is comparing group 1 and person class group 8. So we're comparing groups 1 and 8 that are showing significant differences. And over here to the right will be what item that is, which I'll show you in just a minute. I typically have a piece of paper and I just scan these tables, especially when you have huge groups, and I just write down which groups are different, what's the t-value, p-value, and what item are they different on, and then I'll just have a huge list and figure out, hopefully not a huge list, because you don't want this to happen. But if you have a huge list, then you try to figure out the best way to tell the story. Is it the two groups are constantly different? Is it a certain item that seems to be problematic? And you can kind of figure that out. If there are missing values in your data set, they will show up as a dot. So instead of person class 1, it will be a dot right here. Most of the time, this isn't really that useful, but if there is a reason why somebody would not have wanted to report their demographic information or what class or group that they were in, then that could be interesting. So for example, if you're looking at race differences and you see a lot of differences by the people who preferred not to answer and essentially had missing data, that could be really interesting. There is also a really cool graph that you get if you click a button. And so what this graph is showing is that we've got 4 groups, and the groups are pretty much following the exact same pattern. So we have a little bit of a difference right here on question 15, where you can see this black group and the green group might be a little different, or potentially on 22, this red group and the black group might be a little bit different, but really they're following the same pattern really nicely compared to this picture. So this one has differential item functioning on pretty much every single item except for 13 right here. Everybody is right on track for 13, but everything else is all over the place. So this is not what we want to see. We would like to see patterns that look like this, to where every group is answering and being pretty consistent, not viewing the items differently, answering differently. The whole items are just functioning differently based on some characteristic about the participants. In order to get this, you're going to go to table 30. It's going to ask you right here a drop-down menu for you to choose which grouping you want to look at. If you don't have any grouping options right here, it's because you did not put in demographic or person characteristic things in your syntax. So you would need to create a new syntax that includes the items and now includes all of the demographic information. Then you click this display plot and you can go from there. I usually click entry and label, which is an updated other thing that you'll get right after you click this guy. And then it will open up Excel for you. And so it will open up all of these pictures in Excel. So here's a really great example. This is person class 0 compared to person class 1. This was if they were of Hispanic origin or not. So a 0-1 coding were the only options. And so we would find the Welch t-test probability right up here, scan through for less than 0.01. So we see that 3 rows down. So I'm going to go over. Again, this is only 2 groups, so it's person 0 and 1 are different from each other. Scrolling over to the very far, and I see the CTAQ3, that it means item 3 differs. Functionally is different between persons who identify as Hispanic versus not Hispanic. This is also like a correlation table, or again, like those post hoc tables, where it replicates the information for you. So we're going to see question 3 right here, same information, because now it's comparing 1 to 0 versus up here we're comparing person class 0 to 1. So when you only have 2 groups, you can just look at this first part of the table and you're done. But for the rest of the groups, you pretty much scan and scan and scan and scan and scan. And so you can have group 1 compared to 8, and then at the bottom you'll have group 8 compared to 1. So you're going to get some replication. All right, head over to Winsteps and practice.